Hey guys,
Also,
Biden 25 here.
LOFTID, a technology demonstrator developing a new way to safely bring large payloads through the atmosphere. The final seconds.
Yes, we're watching that in JPSS-2 launch on the final Atlas V from Vandenberg Air Force Base.
Go Atlas. Go Centaur. Go JPSS-2.
There we go, Daryl. Ready for launch this morning.
On a clear night in California, here we go. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2,
Ignition.
1. Ignition.
Liftoff of the Atlas V.
And liftoff. Liftoff of the Atlas V, carrying JPSS-2 and LOFTID, a new weather observatory for our planet, and a test for planetary exploration.
LSPU has gone to closed loop control.
Yeah, it's an Atlas V 401, so no solid boosters.
LSP-100 on its way also. We're very happy for this 100th mission, the Launch Services Program. Let's listen in as Jesse Gonzalez.
And coming up on 30 seconds into flight, vehicle is a half mile in altitude, 2 miles downrange, traveling at 160 miles per hour.
There she goes.
And passing 45 seconds into flight, continuing to see good operating parameters out of the RD-180.
The power of the Atlas V RD-180.
Coming up on a minute into flight, the vehicle is ending its roll maneuver, and vehicle body rates are looking good.
Getting ready and approaching Mach 1.
And passing through 80 seconds into flight, Mach 1 Atlas V is now supersonic.
That's 769.
And vehicle is now passing through max Q, maximum dynamic pressure.
769 miles per hour, 1,234 kilometers an hour. Going through the area of maximum dynamic pressure on the vehicle.
And passing 100 seconds into flight, seeing the RD-180 throttle back as expected. Engine response continues to look good, and vehicle body rates continue to look good at this time.
Throttling down just a little bit to reduce the stress.
Coming up on 2 minutes into flight, the vehicle is now 12 miles in altitude, 7 miles downrange, traveling at 1,500 miles per hour. And passing 140 seconds into flight, the vehicle has gone to closed loop control, continuing to see stable body rates throughout the boost phase.
So the rocket was flying in a trajectory that's programmed in, but now closed loop is taking positional feedback from the rocket sensors to get it into the proper line for trajectory. It's going to maintain that ascent line. Beautiful shot there on board.
And RCS is now pressurizing to flight levels.
A shot from our infrared camera.
And the reaction control system has reached flight levels. System response looks good. Vehicle body rates continue to look good as well. Seeing good response out of the RD-180 engine.
Just everything's going well.
Going to start cooling down that Centaur engine in the second stage to prepare for its super chilled propellants to flow through the booster.
About 3 minutes and 15 seconds into flight, vehicle is now 53 miles in altitude, 67 miles downrange, traveling at 5,800 miles per hour. And now seeing the RD-180 throttle back to maintain a 5.0 G acceleration limit. Engine response continues to look good.
We're just seconds away now from booster engine cutoff.
And we did see a good response on the Centaur systems as it completed boost phase drill down. And we have BECO, booster engine cutoff. And we have successful stage separation.
There it goes. No waiting for the Centaur to ignite.
Now onto the Centaur
on the RL-10. And we have ignition for the first burn. RL10 start parameters look good. And we have good indication of payload fairing jettison.
Great.
Saw a shot of that
There goes the
booster
fairings.
floating off into space.
Yeah, you can actually see the 4-meter fairing going by there too on the video. That's a great thing. Looking at the telemetry data, RD-180 performed very well on the first stage. Separation was clean. Payload fairings, you can see on the infrared video there on the screen, the booster falling away and the two little fairings. Pre-start.
Coming up on 5 minutes into flight, this first burn will be about 13 minutes in duration, the first of 3 burns for today's mission. Continuing to see stable RL10 chamber pressures at the beginning of the burn. And also seeing stable body rates following payload fairing jettison.
RL10's performing very well. Pre-start was good. Ignition came out very well as we saw in the video, and as the Centaur continues to burn nominally, body rates on the vehicle look very good with payload fairing gone. JPSS-2 exposed to the environments of space.
As it warms the motor catalyst beds for operation.
Explain quickly what a body rate is.
So the body rate's the attitude of Centaur as the vehicle is moving through space. We're trying to keep everything as stable as possible. So we have an X, Y, and a Z body rate on the Centaur, and the flight computer and the RCS system continue to maintain that as we move through to get ready for separation.
And now we're moving to ULA's real-time animation.
6 minutes in flight, the vehicle is now 250 miles in altitude, 430 miles downrange, traveling at 9,400 miles per hour.
The animation is informed by real-time data. As we watch the RL10 burn and the Centaur fly, at the top of the vehicle is JPSS-2. And there you're looking at the RL10 as it continues its burn.
And coming up on 7 minutes into flight, continuing to see stable performance across all Centaur systems, stable tank pressures, good performance out of PU, and some minor roll adjustments as Centaur optimizes the telemetry link.
Centaur with plenty of performance to get there.
Plenty of performance and everything's looking great. As we heard Jesse say, everything is performing nominally as we get ready to continue this burn for separation.
We're going to keep watching the data and listening to the launch team as we track the performance of the Centaur getting JPSS-2 into orbit. But in the meantime, let's send it back to Megan.
If you're just joining us, I'm NASA's Megan Cruz, bringing you live launch coverage from Vandenberg Space Force Base along the central coast of California. Just about 7 minutes, 34 seconds ago, we watched as a United Launch Alliance Atlas V rocket lifted off at 1:49 a.m. Pacific time, and it was a spectacular sight. What a clear night. No clouds in sight. That rocket just lit up the dark sky. It's flying 2 important missions today. The primary one is to send JPSS-2 into orbit. It's the National Oceanic and Atmospheric Administration's newest joint polar weather satellite. The secondary mission is called LOFTID, which will demonstrate a new type of heat shield that inflates for atmospheric reentry. We're going to stay with you live for every important mission over the next 2 hours. NASA's primary launch site is Kennedy Space Center in Florida, but we lifted off from California this morning because of the rocket's flight path. By launching on the West Coast, teams kept the rocket from flying over land. JPSS-2 is a polar orbiting satellite which will circle the Earth pole to pole 14 times a day. As the Earth rotates underneath it, it will pass over every single spot on our planet at least twice a day, collecting valuable weather and climate data. Once operational, JPSS-2 will be renamed NOAA 21, and when you open the weather app on your smartphone, you'll be using NOAA 21 data. NASA's Jasmine Hopkins joins us with how the National Weather Service uses the satellites to keep you informed.
Joining us now is Jim Yo from the National Weather Service. Thanks so much for being here, Jim.
A pleasure to be here to talk about JPSS-2 and how the Weather Service is going to use data from it to give the best possible forecast for the nation.
Absolutely. And speaking of that forecast, most of us check the weather before we even leave the house in the morning. So what are the applications of JPSS-2 data?
Well, the Weather Service will use JPSS-2 data as the basis for making numerical weather prediction models run for forecast of 3 to 7 days, but we'll also use those data for making seasonal to season forecasts and to monitor long-term trends for climate science.
Right, and that's great to see that it can help us from day to day and also long term as well, right?
It's very versatile.
Absolutely. And speaking of versatile, I know that NOAA has provided a huge suite of different satellites from JPSS to GOES as well. How does the National Weather Service use them all together?
We use data from the different satellite systems in the Weather Service in complementary fashion. So JPSS-2, by being a polar satellite, will collect data around the world, every spot, twice a day. And that's really important for making a longer-term forecast because today's weather here typically starts somewhere else several days earlier. Now, hurricanes start off the coast of Africa, move to the east coast, or we look in the west coast here in California, and you might see the so-called Pineapple Express storm that comes up, with strong rains from the Pacific that are precipitated in California and other places on the coast. So we use those to get that long-term forecast, but then we use GOES, which are like sentinels on each coast, to provide that fine-scale, up-to-date adjustment in our forecast.
Right. That's great to see how they work together and understand that it's not just local, it is global weather systems, which is huge. So speaking of that, I know that we're all very eager to get the JPSS-2 data in our hands. How soon will it be available to the end user?
Well, the end users will start to see it in forecast in a matter of months. Typically what happens is the instruments on a new satellite will be turned on one by one, and then they'll be checked out to make sure that the instruments are performing as expected, and that the data are what we think they are. We'll compare them to the JPSS-1 data, for example, and then they'll go into the numerical weather prediction models, and so we'll have a seamless transition from one JPSS satellite to the next one.
Right. Well, we're looking forward to seeing that data. That's very exciting. Jim Yo, thank you so much for joining us.
My pleasure to be with you today.
Absolutely. Back to you.
Today's launch marked the second this year, made possible because of the NASA-NOAA partnership. Jim and Jasmine actually just mentioned it. GOES-T lifted off from the Kennedy Space Center back in March. Now renamed GOES-18, it keeps continuous watch over the western U.S., Mexico, Central America, and the Pacific Ocean as a geostationary satellite. That means it rotates with the Earth, remaining in a fixed position in the sky, unlike JPSS-2, which again will fly pole to pole. Having constellations of both kinds of satellites gives NOAA a complete picture of our Earth's weather and climate. JPSS-2 is the third in the latest series of advanced polar orbiting satellites, and boy, they travel fast. It only takes 90 minutes for them to go from the North Pole to the South Pole and back up to the North Pole again. And every time a satellite flies over a pole, it transmits data to two primary ground stations, so you don't have to wait long for a weather forecast. One station is near the North Pole on Norway's remote Svalbard Islands, you see right there. The other is at a station in Antarctica. Antennas at each ground station collect data from the satellites as they pass over. Receivers capture the data, which is then fed into computer models and then to you via weather apps and forecasters. JPSS-2 will do more than warn you of severe weather and help you to plan what you wear each day. NASA's Jasmine Hopkins is back again to show us how the data it collects can also be used to forecast crop yields and how much you pay at the grocery store.
Joining us now is Irene Parker, Deputy Assistant Administrator Systems for NESDIS. Now, Irene, what does NESDIS stand for?
NESDIS is NOAA's National Environmental Satellite and Information Service. And basically what it does is providing satellite and observational data for the nation, specifically for weather and climate.
Wow, okay, a big title. You've got a pretty big job then. So tell me, we understand that JPSS and other satellites like that can help predict the weather, but they can also help us understand rising prices at the grocery store. How does that work?
Oh yeah, people don't realize how much this information from this satellite actually affects their day-to-day lives. So for folks like you and I going to the grocery store and you see those costs of that apple or that banana, that information is really coming from and being supported by our JPSS-2 satellite systems. So the data that the JPSS-2 instruments collect, They're allowing scientists to predict droughts, and it also tracks the greenness of crops. And that information goes into a product called the Vegetation Health Index, and that helps people determine how much food supply the harvest is going to actually produce that year. And based off of that, that determines what that price of that apple, that lettuce, etc., is actually costing us at the grocery store.
Wow, so it's really helping us in that day-to-day life.
It is.
They're also helping us better understand our changing climate. How is that working?
So the way it's helping us with our changing of our climate is that it is providing us continuous data records for the past 40 years. So NOAA has been basically operating polar satellites since the 1980s. So what's really key is that we continue these observations, and the JPSS-2 satellite is going to continue these key observations to be able to monitor the climate change. So basically it's tracking data such as changes in our temperature, sea ice, clouds. It's tracking ocean color information, and all that information is being used by scientists to determine how the climate is evolving. And what it really is also doing is it's actually even taking information above the Arctic, and it's able to see how the Arctic is changing. So you can measure how the change in the sea ices have been happening over the years. And that really helps the scientists and the community to see how climate is changing around the world.
Irene, that is awesome. A lot of great data that we're getting from these. Thank you so much for joining us today.
No problem. Thank you for having me.
Absolutely. Back to you.
We're now just moments away from main engine cutoff. Let's go back out to Daryl Niven monitoring the launch team for us.
That's right, Megan. Thank you. Back here at the Mission Directors Center, joined by Mick Waltman, engineer with Launch Services Program.
Yes,
I'm
Santos
Daryl Nail. As you mentioned, we are tracking the JPSS-2.
A little over a minute remaining in the burn, continuing to see very good performance out of the RL-10.
That's a good sign. RL-10 burning well.
Continuing to see very stable Centaur body rates.
Yep, very stable flight for Centaur through this whole burn. It's about 12 minutes, 51 seconds, roughly somewhere in there, as we get ready to come up on main engine cutoff 1 for this first burn as we get ready for JPSS-2 separation, Daryl. So we've been watching the telemetry live here on the animation from ULA through their SDK. Things look really well.
Yeah, the burn expected to last right around 13 minutes, putting JPSS-2, the Joint Polar Satellite System 2, into its proper polar sun-synchronous orbit. You're looking at animation reflecting real-time telemetry. Just now T-minus 20 seconds until that burn is finished.
And standing by for MECO shortly.
It also,
and we've had MECO 1, main engine cutoff.
You can see that reflected in the animation. We saw a little bit of movement by the reaction control system, which is also reflected here.
And now seeing the RCS system fire at 100% settling.
Yeah, so what the Centaur's doing now is trying to settle the propellants inside the tank. Yep, as we get ready to finish up this burn and get ready for J2 separation about 11 minutes from now. As everything gets ready to go and they start powering up all the systems on the spacecraft, making sure it's all ready to go prior to initiating a separation command.
For a little over 10 minutes prior to JPSS-2 separation.
All right, so that direct inject just a few minutes away. We're going to monitor the progress and continue to do so. In the meantime, let's send it back to Megan.
After JPSS-2 coverage is complete, we will shift our focus to LOFTID, the low Earth orbit flight test of an inflatable decelerator, basically a new heat shield. We will have live commentary of that
an inflatable
right
heat
here
shield
on our broadcast, but right now here with me is Tanya Laughinghouse. She is the program manager for technology demonstrations at NASA. Good morning to you, Tanya. I got to ask you, why is this new inflatable heat shield so unique?
Because it's inflatable.
Well, LOFTID is essentially a test flight of an inflatable heat shield. And all prior flight tests of this technology have been suborbital. So that means they go up and then they come back down. Well, today's test will actually be orbital. So we'll do a full orbit around the Earth and come back. And once it does that, the energy is going to be so much greater. And so we're really excited to see how it performs at orbital velocities.
And how could this technology be a game changer for future missions into deep space?
Well, absolutely. So when we're trying to land a spacecraft into the thin atmosphere of a planet like Mars, we need a really big heat shield in order to slow it down safely. And previous heat shield diameters have typically been limited to the size of the vessel that it's launching in. And so what's so great about LOFTID is that its heat shield is pliable, so you're able to fold it and compact it very tight into the spacecraft. And so that means you have additional room for other high mass items that are needed for crewed mission to Mars. Items like oxygen sensors, like entry vehicles, habitats, rovers, etc.
So I see the space applications, but you and I were also talking about this earlier, that there are Earth applications for this technology as well.
Absolutely. So in NASA Space Tech, we love to say that technology drives exploration. But another huge objective for Space Tech programs like Technology Demonstration Missions Program that I manage is that they are directly aligned with NASA's strategic objective to develop technologies that improve the quality of life here on Earth. And a prime example of that, Megan, to your question, is the spinoff tech from the heat shield materials, the materials that we make the heat shields. NASA and the U.S. Department of Agriculture developed a prototype to improve a fire shelter that protects firefighters, and it's made from the actual materials that come from LOFTID.
Tanya, thank you so much. I love when we can draw those parallels again, how we could use things in space, but also the same technology here on Earth. So thank you so much for that. And at the top of this broadcast, we told you today's launch was LSP's 100th mission. As we mark this milestone, team members look back at some of the missions that got us there.
Status check proceed with current count.
And now coming to us through downlink from Teeter 7.
Rock formation.
2 minutes.
Inlet 5002 T0 land for 0205.
And liftoff.
You never forget your first. And my first mission I worked was the demonstration of autonomous rendezvous technology. Basically, it was demonstrating the technology of autonomously docking to spacecraft in space. At the time, I didn't really understand or know what that technology was being used for, but now that technology is being heavily used today.
My first assignment was Lucy as a backup integration engineer. I felt overwhelmed at first, but I started to realize I had the full support of my management team. I had all of their years of experience that I could count on as sort of standing behind me. We hit our mark. We launched on the first second of our planetary window that we've been targeting for over 3 years.
Sojourner was my very first. Ever since that mission, I've been a part of every other rover that has landed on Mars. Spirit and Opportunity, I was also the launch director for MSL and Curiosity. So those are always something that I could look back and say, wow, I was fortunate enough to be in the right job, to be able to do this and do my little part to make that happen.
After experiencing my very first LSP mission, I think is when reality hit me that I get to be a part of this incredible team that's making history, really, and is helping all of humanity, which is amazing.
The heat shield test we'll see later today is led by NASA's Langley Research Center in Hampton, Virginia. Let's head back over there with NASA's Angelique Herring, who's with the LOFTID team. Angelique, tell me, what are they preparing for now?
Okay, I'm going to the here on bottom 25. I've got some other stuff to do. Goodbye.